All right, so for this problem, the family's going on a road trip, everybody grabbed a bunch of different stuff. Would it make sense for us to say that they have, let me do a little bit of quick math here, 2,100 and a little bit more quick math, and 16 entertainment options? Would that be the way that you would describe this information? Probably not, right? Because, well, we could just kind of add them all up together. That's not the way we normally talk about it, right? Normally, we'd look at, okay, well, they ended up bringing 2,100 songs. And then they brought some movies as well, right? So they ended up bringing 10 movies. And then they brought some games. They had 1 game and 5 games, so they had 6 games. This is the more typical way of describing it, right? Because we break it down into the individual things, because each of these provides for a different purpose. The songs are going to be used at a different time than the movies, and they're going to be used at a different time than the games. And so we break it up and we describe it as things that are like each other. We don't just clump everything into one big category, right? Okay, I'm going to go with this idea a couple more times because I really want to reinforce it, because I'm going to make it mathematical on you here in a moment. So take a moment, read through this situation then. All right, so if we now go and answer this question, and I actually wanted to add them up. Am I going to add the 85, the 12, and the 18, the 62, 3, and 25? Am I going to add all 9 of these numbers together into one big number at the end? Yes. I don't think that would necessarily make sense. Because if you did that, we get some ugly number. I'm not going to do that calculation right now. But we get some big number. And it'd be saying, let's say that it gave us an answer. I'm making it up here. Let's say it gave us an answer of 300. Would we say there was 300 junk?
Yeah.
It's kind of awkward, right, to say that. And because we tend not to say there's 300 junk in the drawer, we would be more likely actually instead to say, okay, let's count how many pennies were in the drawer and count those up. And then we might count up, okay, how many total buttons are there in the drawer? And then we might go to, okay, how many total batteries were there? And then that actually tells us more detail about what's going on with that stuff in the drawer. If we clump it all into one, it doesn't give us the same information. And again, one more of this type. Please take a moment and read through this one. All right, and as you might expect from the previous two that we are doing, we can really figure, yeah, I'm going to need to group the ones that are like each other. So like, when I total up how much supplies they have, I'm going to combine all the pencils together into one number. So I'll do the 2 plus 8 plus 1 plus 12. And that tells us that they have 23 pencils. Okay, no problem. But now this is where things get interesting from here. Because next up we have sheets of paper and we have reams of paper. Now, are we told how many sheets are in each of these reams? No, we don't know that. Now, they're both talking about paper. But because I don't know how many sheets are in a ream, I can't just combine the sheets in the ream here. I would still have to treat each one of those separately. And so I'd have to total the number of sheets of paper. And then I'd have to go through and combine any numbers of reams of paper from there. Even though they're still talking about paper, sheets of paper and reams of paper are going to have to be counted differently because we don't know how much is in a ream. And with that idea, that actually combines over into the ideas of math and variables, because we don't know what a variable equals unless we're told it. And so a variable can equal so many different things. And so, let's actually take a look at a math problem here. So, kind of weird the way we're saying it here, but this is really what we do in equations. So, A has 8 x's, and they have 10 x squareds. I'm asking here, what's the total? And so again, we have to think about, okay, the x's, I can't say that they have 18, that A has 18 things. A has 8x's and 10x squareds. So if I'm going to describe a total, I'm really going to see how many x's are there total amongst this. And so you notice I underlined them in blue there. There's a total of 12 x's. We can do the same thing with the x squareds. So the 10x squareds, the 15x squareds, and the 9x squareds there. Now notice, they're all talking about x's, right? But the first one is just plain x's. The next one is x squareds. Even though they both have x in them, I can't combine them. Just like when we're doing it with the paper and the reams of paper, they both had paper in them, but we didn't know how many sheets were in a ream. Just like in this case, I don't know how many x's make up an x squared here, because it's going to change depending on what x equals. And so we can total all those up, and we can find out that there's 12 x's, 34 x squareds, and 20 x cubes, doing the same basic method as what we did in the last problems. But of course, I'm talking about x's here, right? So I can actually represent this mathematically as well. I don't have to write x's in quotations like this, and x squareds in quotations. We can actually write them as x's and x squareds like that. That's why we have the symbolism. It's a lot easier to write it, a lot shorter. And so really what I did is I took all of this information up here and wrote it as an expression. And in fact, I could even take what I started with and think of that as expressions. Because really that first one was saying that we start with 8x and 10x squared. That is 8x plus 10x squared. And the second one, they have 4 x's, 15x squareds, and 7x cubes. And so on. Which actually, if we wanted to, we could even just turn all of this into a single math. And we could write it all out just as what the first person had, plus what the second person had, plus what the third person had. And notice that we can get this answer. But it's again because I have to look for the things that are like each other. So I can combine the x's, remember. So I look for anywhere where there's just a plain old x, and I combine those to get that. Then I look for the x squareds, and I can add all those up together to get the x squareds. And of course the same thing then for the x cubed terms. The 7x cubed and the 13x cubed gives me 20 x cubes. And so what we were talking about to start with, like the pencils and the paper and the reams of paper and all that stuff, that's exactly what I'm asking you to do when I give you something like this. When I give you some big long thing that has x's, x squareds, x cubes, all that kind of stuff in it, all we're doing is trying to find a shorter way to describe it. Let's combine the things that are like each other. Now typically we talk about that in terms of, or in the words of, like terms, right? And oftentimes we get a little mixed up with that. It's one of those things that people talk about, math teachers talk about all the time, but outside of like one day in 7th grade or something like that, we never explain. So, if you were gone that day in 7th grade, we can make sure you now know what this means. Please add this into your notes. All right, so a couple little notes here along the way. Terms, that's another one of those words that we tend not to use and explain a lot. So basically, if you have some big, long expression with lots of things that are added and subtracted, the terms are just all the different pieces that are separated by the addition and the subtraction. And I'll look at an example of that here in a moment. So that's why we get this phrase of like terms, because they are terms that are alike. That is, they have to have the same variables, and the exponents all have to be exactly the same as well. All right, now a little note down here. We can add or subtract only if the two terms are like terms, which we normally call combining like terms. But we can still multiply them, even if they are not like terms. All right, sometimes people get that mixed up. We can only add if they're like, but we can multiply no matter what. All right, let's look at an example of this in action. So go ahead and write down this example, and then go ahead and combine the like terms on your own first, and then we'll do it together. All right, so if I'm going to do all this addition, subtraction, that means I'm looking for like terms. Now remember that the terms are separated by addition and subtraction. So every single one of these is considered a term. So this particular expression happens to include a total of 6 terms. Now, I said to write out the original problem and your answer. When you have the original problem written on your paper, it also allows you to do some things that make your life a lot easier. For instance, you can mark each type. So for instance, I have a x and I have an x there. So I put squares or rectangles around the plain old x terms. Okay, the next thing I encounter is an x to the 4th. I'm going to circle anything that has an x to the 4th in it. It's just an arbitrary choice of what I'm marking it with, but I'm marking them the same. And then I need to mark the x squareds in some way. I'll underline those. How about that? I'll underline the x squareds. And by doing that, you make an easy way to visually find what you're looking for. One other little detail, one other thing that this can do for you, is notice when I circled them and marked them and stuff like that, I included the plus in front. Because let's say that this was a minus instead. If this was instead a minus, that means I would treat it like it was a negative 3x to the 4th or minus 3x to the 4th. It would help me remember that I'd be subtracting that instead of adding it. So these little things will help you keep track of it all. All right, now we can go ahead and do it. Now the one thing I expect might have caught you off guard in terms of how do we actually do it is actually the very first one. This 6x plus the x. Because that x is just x. Well, there's an invisible number in front of the x, right? What is the invisible number in front of x? 1. So that x is the same as 1x. So when I do 6x plus x, I'm really doing 6x plus 1x, which means I have a grand total of 7 x's. In other words, I took 6 x's and I added an x to it to get 7 x's. All right, next up. Next thing I come across is the x to the 4th, so I will do that. If I have 8x to the 4th and I add 3x to the 4th, that gives me a grand total of 11x to the 4th. Notice that by them being like terms, the variable and the exponent do not change. That's why they have to be the same. And by the way, big universal math rule right here. A great one that you can remember that basically works all the time. If two things have to be the same, it's because they're going to stay the same. So like if the exponents have to be the same for me to do this, it's because the exponent's going to stay the same after you do it. All right, last one, we do the x squareds. I got 4x squareds and I'm adding 9x squareds. That gives me a total of 13x squareds. And so that's what you're looking at for your final answer. Now if I want to start by marking it again, I'm going to just go ahead and just start with the first one. So I got an x cubed there, so I'm going to choose to put a box around that one. So then I go and look for any other x cubes. All right, so I got an x cubed here. And do I put a box around this one?
No.
Should I have that?
No. It's got.
Well, it does have an x cubed in it.
But it also has a y.
Yeah, but it also has that y cubed, right? Well, let's deal with the y cubes then. Okay, so y cubed, chose to circle those. So then, what do I do with that x cubed, y cubed? Because it has the x cubed in it, it also has the y cubed in it. Can I combine it with both? No. What can I do then? Well, in this case, nothing. That x cubed, y cubed, in order for me to be able to add or subtract this with anything else, I would have to have something else that had both x cubed and y cubed in it. That was the tricky one about this. All right, now, when you add all those like terms together, you should get 8x cubed plus 10y cubed plus 10x cubed y cubed. Now, second phase of what we're talking about through this work here, is this an expression or is it an equation? Yes, it is an expression. Now, how do you know? Exactly, very good. There's no equal sign. A lot of times, we get a little sloppy with our language, and we call equations expressions, or expressions equations even more. I'm even guilty of that at times. And so I want to make sure that we have this totally down. So, more notes. Expression and equation. What makes what? Now, you can shorten these if you want to a little bit. You know, this last sentence is critical though, so I want everyone to be writing this into your notes. At least the word and that last sentence for each one, please. Now this vocabulary, this is a little bit easier for us to keep down. We tend to be pretty good with knowing whether something's an expression or equation. We just get a little sloppy at times maybe, right? But let's say we're going and solving something. Can I solve both of these, expressions and equations? Well, this is where we start getting past just being a little sloppy and actually missing a little bit of understanding about what we do mathematically at times. Because you can actually only solve an equation. You cannot solve an expression. Because in order to solve something, we have to figure out what a variable equals. And if there's no equal sign, we can't figure out what it equals. And so, a few more important pieces of notes here. What can we simplify? What can we solve? So as we take a look at this, the first question is this an expression or an equation? It is an expression. Very nice. Because, again, there's no equal sign, so it's got to be an expression. All right, so can we simplify it or can we solve it?
Simplify.
Yep, we can simplify it then. We cannot solve it. All right, so then let's simplify it. That means combining like terms like we were doing earlier. And so I got some x's, I got some x's, and then I got some numbers. Now notice the numbers don't have x's in them, and so they got to be treated separately. So this whole thing just ends up being 8x plus 10. All right, easy, right? Okay, let's make one small variation to that. What if I gave you this problem now? Is this an expression or equation? Yep, now it's an equation because it has that equal sign. All right, so if I give you an equation, am I going to simplify it or solve it? Yep, we're going to solve that. And so let's go ahead and solve this one. Quick refresher on that. That means moving stuff from one side to the other. And so you notice that part of what this does then is this tells us and gives us hints about what we should do with the problem. When we have an equal sign, we're moving stuff side to side. But without an equal sign, all I can do is combine like terms. That's all. I can't do anything else along the way. So that's the solving. Notice that a solved equation looks like this sort of a thing. X equals 4. I can't do that if there's no equal sign. I can't solve it like that. All right, one last one. This one, I want you to write this one down and do it on your paper, please. All right, so first thing, let's actually deal with those two questions up at the top. Is this an example of an expression or an equation? Yep, this one's an equation because we got the equal sign, remember. That's all you need to do is just identify equal sign or not. And then, so then are we going to simplify it or solve it? We're going to solve it, yes. But you'll notice that in this case, our solving starts with simplifying. And so in order to start solving this equation, I'm going to simplify what I can, which means distributing in this 4 first. So we got 4x plus 16 equals, and now on the right side, I can simplify that by combining like terms. And so there I can do the 5x plus the 2x. Let's actually mark those here. So 5x and the plus the 2x. And so that's going to give me a 7x. And then for the next part, I have the minus 8 and the plus 9. Here we actually have a minus involved. And you can see the advantage of circling the sign in front of it as well. Because I know I'm doing negative 8 plus 9 then. And so that's going to actually give us a positive 1. So you should have 7x plus 1 there. Because again, negative 8 plus 9. All right, and now we solve like we normally would. So I'm going to subtract the 4x from both sides, because I like to keep my x's positive. That means I got to now subtract the 1 from both sides. And finally, divide both sides by 3. And you end up getting that 5 equals the x. And this thing won't let me write that down. Let me move that up just a little bit so I can actually write it. No, that's just wrong. 5 equals x anyway.